अपनी में से चलो।
घर पे चलो।
चलो।
सीधे चलो उधर।
Hello friends, can you guess how many molecules will react without any information about the molecules themselves? To know that, we must first know how molecules are structured. This is why smart people have developed theories that tell us how these molecules are structured. Learn one of these theories by watching this video. Coordination complexes were known and studied by chemists from the mid-19th century. However, there was no clue about their structures at that time. In the year 1893, a Swiss chemist, Alfred Werner, proposed the first workable theory of complex ion structures and their formation, known as the Werner's theory. He proposed that in the complex hexamine cobalt-3 chloride, the CO3 plus ion is surrounded by 6 ammonia molecules located at the vertices of an octahedron, while the 3 Cl minus ions are dissociated as free ions. Werner's proposition is based upon his extensive experimental work with complex compounds of cobalt-3 chloride and ammonia. Werner prepared different compounds composed of cobalt-3 chloride and ammonia, all of which had different colors and were thus named accordingly. Note here that these are not the present-day IUPAC names of these compounds. All these compounds contain ammonia, and thus he reasoned out that just like ammonia gets dissolved in dilute hydrochloric acid to form ammonium chloride, aqueous solutions of these compounds must react with dilute hydrochloric acid to form ammonium ions in solution. However, to his surprise, he found that none of these compounds reacted with HCl even at a very high temperature. Based on this observation, Werner proposed that ammonia molecules are bound very tightly to the central cobalt ion and cannot be released as ammonium ions readily. Next, Werner tested all his solutions for the presence of chloride ions. As we already know, when a solution containing chloride ions is reacted with excess of Ag plus ions, the chloride ions precipitate out as AgCl. Accordingly, Werner reacted all the 4 compounds with silver nitrate and analyzed the results quantitatively. He found that while 3 moles of chloride ions were precipitated for 1 mole of COCl3, 6NH3, 2 moles of chloride ions precipitated from COCl3, 5NH3, while only 1 mole of chloride ion precipitated out from COCl3, 4NH3. This led him to the conclusion that not all chloride ions bound to the central metal ion are ionizable. Only those ions which are ionizable precipitate out as silver chloride. Werner named these valences as primary valences. Werner called the parts of the molecule which were not ionizable and were held strongly to the central ion by coordinate bonds as the secondary valences. The words primary and secondary, however, no longer bear the same importance. In the present context, primary valence is equal to the oxidation number of the central metal ion in the complex, while secondary valence is equal to its coordination number. Werner's theory also throws light on the structure of these complexes. While the primary valences are non-directional, secondary valences to the metal have characteristic spatial arrangements, and this arrangement assigns a specific geometry to the coordination compound. Accordingly, he postulated each of these complexes as an octahedral. Let's summarize. According to Werner's theory, the central metal ion in coordination complexes possesses 2 kinds of valences: primary valences, which are ionizable, and secondary valences, which are non-ionizable. Primary valences are non-directional, while secondary valences impart a specific geometry to the complex. A molecule or coordination compound is only as good as the parts it's made from. Kind of like your favorite sandwich. Find out more about these incredible molecules